Hello children, once again welcome back to Physics with Sanoobs. See, in this video we will be discussing all the neat previous questions from the chapter Mechanical Properties of Solids or Elasticity. First question, let a wire be suspended from the ceiling and stretched by a weight W attached to its free end. The longitudinal stress at any point of cross-sectional area capital A of the wire is. That must be W divided by A. Okay, because stress is force divided by area, and there are two types of stress, normal stress and tangential stress. Okay, and here the stress is normal and it is weight per unit cross-sectional area, W over A. Now next, a wire of length capital L, area of cross-section capital A is hanging from a fixed support. The length of the wire changes to L1 when a mass M is suspended from its free end. The expression for Young's modulus. See, Young's modulus is normal stress by linear strain actually. Normal stress is the force applied per cross-sectional area. So it is F by A, or here F is mg. So mg divided by capital A is the normal stress. And linear strain is change in length divided by original length. See, original length was capital L. Now the length is L1. So the increase in length is L1 minus L divided by original length, that is the linear strain. So we will get Young's modulus mg capital L divided by A into L1 minus L. mg capital L divided by A into L1 minus L. Alright. Next, two wires are made of the same material and have same volume. The first wire has cross-sectional area capital A and the second wire has cross-sectional area 3A. If the length of the first wire is increased by delta L on applying a force capital F, how much force is needed to stretch the second wire by the same amount? Okay. Now see, a force that is equal to YA by L, that is the original length, then increase in length delta L. Okay, and see, F equals Y, multiply both the numerator and denominator by cross-sectional area A. So we will get YA square delta L divided by AL. See, this AL is actually the volume, right? This is the volume of the wire and it is same for both the wires. Okay, and same elongation is to be produced in both the wires. Okay, A into length, volume is same for both the wires. Elongation is same for both the wires, and both the wires are made of the same material. So Young's modulus is also the same. So we can say F is directly proportional to square of the area. So F dash over F will be A dash by A whole square, and A dash is given as 3A. So it will be 3 square or 9F. Okay, so it must be 9F. Now let's see what we have next. The Young's modulus of steel is twice that of brass. Two wires of same length and same area of cross section, one of steel and another of brass, are suspended from the same roof. If we want to lower the ends of the wires to be at the same level, then the weights added to the steel and brass wires must be in the ratio. Now see, Young's modulus, that is stress over strain, and we can write FL divided by A delta L, where L is the original length. Okay, so here we will get F equal to YA delta L by L. Here elongation produced in both the strings or the wires are the same, and their cross-sectional areas are also the same. Okay, the original length is also the same. So we can say the force required is directly proportional to Young's modulus. Okay, and Young's modulus of steel is twice that of brass. Okay, then the weights added to steel and brass will be in the ratio 2:1. Okay, so it must be 2:1. Right? Now here we can say, see, force for steel divided by force for brass. This is equal to Young's modulus of steel divided by Young's modulus of brass, and this is equal to 2 or 2:1. The following four wires are made of the same material. Which of these will have the largest extension when the same tension is applied? See, here we have delta L. Elongation is FL divided by cross-sectional area pi d square by 4, then Young's modulus. Or we can say elongation directly proportional to L by d square. Okay. Now see, in the first case we have 100 centimeter and diameter is 1 millimeter. So 100 by 1 square, we have to see, just compare the ratio L by D square. So you need not convert this millimeter to meter or centimeter. Okay, so first will be 100 by 1 square, second will be 200 divided by 2 square, and this will be 50. Okay, this will be 100, and this is that will be 100 divided by 3. Okay, and here it will be 200. So this is the maximum. Okay, here we will get maximum value. So this must be the maximum, right? Now two wires A and B are of the same material. Their lengths are in the ratio 1:2 and the diameters are in the ratio 2:1. If they are pulled by the same force, then the increase in length will be in the ratio. See, delta L here we have FL divided by AY. Cross-sectional area we can express like pi d square over 4. So we can say delta L directly proportional to L by d square. So delta L1 by delta L2. Okay, their lengths are in the ratio L1 by L2, that is 1 by 2. And their diameters are in the ratio 2:1. But here we have d2 by d1. So it will be again 1 by 2 whole square. So that will be 1 by 8 or 1:8. Now see, when a block of mass capital M is suspended by a long wire of length capital L, the length of the wire becomes capital L plus small l. Means small l is the elongation produced. The elastic potential energy stored in the extended wire will be. See, the elastic restoring force developed in the string, that is given by F equals YA elongation divided by original length. Okay, now this YA by the original length, that can be replaced by the force constant K. So we can write F equal to KL. Okay, just like in an elastic spring. Okay, the elastic potential energy stored, that is half KL square. At equilibrium, this mg, the force with which the string is stretched, that will be equal to K, force constant into elongation. And the force constant we can rewrite mg over L, where mg is the force applied and L is the elongation. Elastic potential energy half KL square, this is half, and K is mg over small l, then L square. It is half mgl. Okay, so this must be the energy stored in the elastic string. Okay, next step, the bulk modulus of spherical object is B. If it is subjected to a uniform pressure P, the fractional decrease in radius is. Okay, now see, volume is 4 by 3 pi r cube. So we can write V raised to volume raised to 1 directly proportional to R raised to 3. Okay, now then this power 1 into delta V by V, that is equal to this power 3 into delta R by R. This is the fractional change in volume and this is the fractional change in radius. Okay, now see, bulk modulus is equal to applied pressure divided by volume strain. Okay, and this negative sign is to show that when the pressure is increased, volume will be reduced. Okay, so here we will get delta V by V equals minus delta P, that is the applied pressure, over bulk modulus. Here the applied pressure is given as P, so minus P by B, where B is the bulk modulus. Now this delta V by V, okay, that can be replaced by 3 delta R by R. The negative sign on the right side that I have taken to the left, so I will get P over B. P is the applied pressure, B is the bulk modulus. Okay, now this minus delta R over R, that negative sign is to show that radius decreases. So the fractional decrease in radius will be P divided by 3B. So P divided by 3B, this must be the correct option. Okay, now let's see what we have next. When an elastic material with a Young's modulus Y is subjected to stretching stress S, the elastic energy stored per unit volume. Okay, see, this is the formula for energy per unit volume, half Young's modulus, and this is a small letter sigma and it represents strain. Okay, so we can write this, see, energy density. Okay, Young's modulus into strain. Young's modulus, split this sigma square into sigma. Then Young's modulus into 1 sigma. That will give you the stress. So half into stress into strain, that will give you the energy per unit volume. Okay, because this Y equal to stress by strain. Okay, and sigma will be stress over Young's modulus. Okay, so energy density U, that is equal to S by 2. Okay, this is S by 2. Then sigma I can rewrite as S by Y, where Y is the Young's modulus. So we will get S square over 2Y. Okay, S square over 2Y. This must be the correct option. Okay, and this is a beautiful relation that you should know, the energy density in an elastic string, that is equal to half into stress into strain. Okay, now children, we have discussed all previous questions for NEET from this chapter. Okay, see, only this level of questions, this type of questions you need to expect from this chapter. Thank you.